Now what we're going to talk about is what is called polarity. Let's talk about polarity here. So guys, polarity, first of all, what does that mean? I did talk about electronegativity to you guys. Remind me, guys, if I'm giving you a bond between C and O, can you tell me which way should I make the arrow? You guys remember that?
Going to the
We make it towards more electronegative or less electronegative. Like, who is stronger between C and O if there's a fight for these two electrons?
Oh, you go back to the chart, right?
What's that? You look at the chart, yes. So you go to the chart.
Oxygen. It goes towards oxygen.
Yes, because you see here, oxygen is 3.5 and carbon is 2.5. So if I go back here, if I label them, carbon is 2.5 and oxygen is 3.5. Okay, now that I'll be looking out towards the oxygen because it's more stronger. Okay, now is this a covalent bond or ionic bond? CO bond.
It's covalent.
covalent.
The covalent bond. So guys, is this electron from carbon being taken away from oxygen or is it just sharing?
Sharing.
Sharing.
So that electron is just sitting there. But oxygen, being more electronegative, being more stronger, is able to pull this carbon's electron more towards itself, right? Now, when this happens, guys,
Sharing, right?
what's that? It's still sharing, yes. This electron still is in carbon's territory. This electron is still in oxygen's territory, but oxygen is trying to pull it towards itself. Okay, it's not
like a magnet, kind of.
Yeah, like a magnet, yes, because it loves the electron so much. Okay. Now, whenever you see, did I talk about the differences in electronegativity, guys? Again, I'm lecturing this couple of different sections. So I want to ask you.
Not sure I remember.
Like, did I give you this table that from 0 to 0.4?
No.
Okay. All right. Okay, so let's talk about this table for deciding the bond polarity, okay? Now, the difference in electronegativity is what we are talking about here. So there's a range of difference in electronegativity, 0 to 0.4, 0.5 to 1.8, and then anything more than or equal to 1.9. So these are three ranges that we got for our difference in electronegativity. So what I'm trying to ask you is, tell me between C and O, what is the difference in electronegativity?
5.
What's the difference? So this is 3.5.
Be 1.
The other one is 2.5. So the difference is 1.0, right? Now tell me, where does that fall? That falls
Right
under
there in the second one.
or the second one or the third one?
Second one.
Falls under the second one, right? So our CO bond falls here. Now, what are these bonds called? So guys, look here now. When you're going to complete this table, when the difference is between 0 to 0.4, when the difference is very little in the electronegativity, we call those bonds non-polar bonds. It's a non-polar covalent bond. It's still a covalent bond, but it's non-polar. So guys, when we say polar, non-polar, what do we mean? Polarity, like North Pole, South Pole, you understand that it's not a magnet, but what we're trying to say is that when two things are poles apart, that's what we're talking about. So when the things are similar in their electronegativity, they're non-polar, okay? But when the things are very polar, when their electronegativity difference is big, and by big we mean it's between 0.5 and 1.8, those bonds are considered polar covalent bonds. Now guys, when the difference is more than 1.9, so guys look here on the screen.
Okay.
So when the difference is more than 1.9, now again, I'm just gonna say, imagine that there are two atoms, A and X, and this guy is let's say, let's say this guy is 1.1, and this guy is 4. Now, what is the difference here? What's 4 minus 1.1?
2.9.
2.9. So you see 2.9, that difference in electronegativity is too big. And when that happens, guys, this X is so much stronger than A that it actually takes away the electron from A. So guys, when the electron is taken away from another atom, is that still a covalent bond or is that ionic bond?
Ionic.
Ionic.
So guys, whenever the difference is more than 1.9, you're gonna consider that to be an ionic bond. It's no more covalent. So guys, based off the previous definition, the preliminary definition that we learned of ionic and polar, which was metal, nonmetal, and nonmetal, nonmetal, this is a more sophisticated definition.
We just do some classes on that one.
Yeah. So technically, if metal, nonmetal, nonmetal, nonmetal does not answer our question, actually the difference in electronegativity should answer the question if our bond should be ionic or if it should be covalent. You see, covalent are two types, non-polar and polar. Okay. All right, guys. Again, any questions so far?
So what does polar mean?
So polar means when you have two atoms like the C and O, and let me draw this again. So let's say you have C and O. Oxygen is so much stronger than carbon that it's pulling the electron more towards itself. Guys, what is the charge of electrons? Positive or negative?
Negative.
It's negative. So guys, if the oxygen is so strong that it's able to pull away the electron, that means trying to pull the electron away from the carbon, that is going to give you some partial negative charge on oxygen and some partial charge on carbon, positive charge on carbon. This partial positive, partial negative charge difference, this is what is called the polar bond or polarity. Okay. When there is like a positive and a negative end to an atom, to a bond, that's what we mean by pole or polarity.
Thank you.
Can we do another one, please?
Yeah, sure. We'll do. So let me give you one more example. NS. Tell me which way should I make the arrow and classify if this bond is polar or non-polar.
The arrow pointing to the
N.
sulfur.
So let's see. We have to look at the numbers. So nitrogen is 3 and sulfur is 2.5.
Oh,
Nitrogen is 3 and sulfur is 2.5. So guys, you do not always make the arrow towards the one who's on the right hand side. You have to look at the numbers. So now guys, which way should we make the arrow?
To the left.
To the left, towards nitrogen, right? Now, will you call this bond polar or non-polar?
Polar.
It's going to be polar. Why is it polar? Because when you found the difference, guys, for difference, we use this triangle symbol, which is the symbol for D in Greek, like delta. So difference in electronegativity is 3 minus 2.5, which is 0.5. And 0.5 falls under the second category, which is the polar covalent. So you're going to call that this bond is polar covalent bond. Okay?
okay.
Does this also work for the ionic bonds also?
Yeah, so if you had something ionic, yes, this will work. So you'll be able to, so let me give you an example. Lithium and then chloride. So lithium is 1 and chloride is 1 and chloride is 3. So now tell me, what is the difference in electronegativity?
2.0.
So it's 3 minus 1, so that's 2.0. And 2.0 is under the table. 2.0 means what? It's ionic. You see, if it's more than 1.9, that's ionic. So now this bond that we were talking about, LiCl, this is an ionic bond. And we already knew that because remember, lithium is a metal and chlorine is a non-metal. So if you have metal non-metal, it should be ionic, and this table confirms that.
Okay.
So they're not trying
Also,
to
the
say
math is
what's that?
the math is still there. That makes it ionic.
What is still there?
The math that's part of it, like that turns it into a covalent bond, is there because the is smaller than the other one.
Yes. So the actual reason behind metals and non-metals giving you ionic compound is this: because metals want to lose the electron. Why do they want to lose the electron? Because their electronegativity is too small. Why do non-metals want to gain the electron? Because their electronegativity is too high. And when that difference is good enough, and by good enough we mean more than 1.9, then yes, the exchange of electron takes place. One gives away the electron, the other one takes it.
So we don't draw the arrow anymore?
I mean, you can draw the arrow if you want to, but usually you only do arrows for covalent bonds. But it's not.
Okay.
Thank you.
Okay. So on the example, I'm going to ask you to make the arrows. I only do that for covalent compounds. Okay. Because you see in lithium, actually lithium has become complete +1 and chlorine has become -1. So you can show that as well. Okay. All right, now the point is what, guys? Why we are learning polarity today is because we want to see how we can tell if our molecule like CO2 is polar or non-polar. Okay, so this is the part you want to listen to very carefully. This is the confusing part. Okay, now once you have your structure, tell me, what was the shape for this molecule?
Mm.
It was linear based off what we learned. It was 220, so that's linear, and the angle was 180 degrees. Now comes the question. There are two questions, guys. One question is bond polarity, and one question is molecular polarity. If the molecule is polar or non-polar. They're two different things. So bond polarity simply comes from you finding the difference between the electronegativity, and that tells you if the bond is polar or non-polar. That is very simple.
Your mom?
Yeah. You have a question?
No, sorry. No, he said mom.
Okay, oh man. All right. So for bond polarity, that one is sorted. For CO, we already know, what was it, guys? Polar or non-polar? So CO bond is polar or non-polar?
Polar.
It was polar. We figured that out earlier because the difference was 1. Now comes the molecular polarity. This is the part, guys, where you need to look at two things. You need to look at the bond polarity again, for which you already know the answer. Yes, it is a polar bond. But then you have to look at one more thing, which is called symmetry. And symmetry can sometimes be confusing, okay? So first of all, let me tell you guys, what are we trying to do here? What we're trying to do is we're trying to figure out if the molecule is polar or non-polar. First of all, why do we care about that? Now, if you guys have taken a biology class, you might have learned if the water is considered polar or non-polar. What is it considered, guys? If you
Polar.
water is
Polar.
H2O is a polar molecule, and what do you guys think about fat? Does water and fat mix? Like
No,
water or
but,
oil mix? They don't mix. Water is
non-polar.
polar and fat is actually non-polar, guys. That's why they don't mix. It's a very, very important property that we need to understand about these molecules. And this also will tell you why are we washing hands so many times these days? So why just water is not good enough? Okay, so there are things that are soluble in water. There are things that are soluble in fat. And if something is soluble in water, it's not going to be soluble in fat. If something is soluble in fat, it's not going to be soluble in water. Does that make sense? So if you have something which is polar, it will dissolve in something which is polar. Let me give you one example, okay? Glucose or sugar is polar. Does it dissolve in water, guys?
Yes.
Yeah.
Yes, it does. Like if you mix sugar and water, it does mix, right? That's what we're trying to see. When you take sugar, you put it into water, it mixes. Water is polar and sugar is also polar, so that works. Does oil mix in water? No, it does not.
Oh,
Because water is polar, but oil or fat is non-polar. Does that make
Does
sense?
it have to float though? Because you know how oil and fat float above water. Does it have to float?
I mean, that
Like
depends on the
non-polar
density.
also.
See, if it floats or if it sinks, that depends on the density. Remember, you guys did the density lab. If the solid is going to stay on the top or on the bottom, that will depend on the density. So what we're trying to talk about right now is if they mix together, like they disappear and you cannot tell which one is which. Okay, that is what we mean by mixing. So not if it floats or sinks. See, if it's floating or sinking, both of those things mean that that thing did not dissolve.
Or heterogeneous or whatever
Yeah,
it's called.
homogeneous and heterogeneous, exactly.
Heterogeneous.
Yeah, so heterogeneous is when things don't mix, right? That's when you think about if they float or if they sink.
Okay.
So polar, non-polar, they don't mix with each other. So that's why, guys, like for any virus or any bacteria, anything living, their cells, what is that covering called, guys? What is the cell covering called?
Nucleus?
No. The covering of
The
the
lipid membrane.
Lipid.
the membrane, the lipid membrane, right? The plasma membrane, the cell membrane, or the lipid membrane. You see, it's lipid. Lipid is fat. So the membrane, guys, is made up of fat. So do you think if I have virus on my hand, hopefully not, if I have the virus on my hand, then it has its cell, right? So that cell has a covering of lipid membrane, of lipid.
Mm-hmm.
Do you think if I put my hand under water, that that fat globule or that fat cell is going to remove, it's going to be rinsed off from my hand?
No.
No, it won't. What do you need for that? You need
Soap.
some kind of soap, because soap is good at dissolving in water as well as fat. That's why soap is so good at cleaning. If you have oily hands, then you want to wash them with, not, water is not going to work with oil. You need
Yeah.
when you use the soap, it solubilizes fat. So that same thing happens with any bacteria or virus, whatever that you're trying to kill. Anything that has a living thing has a cell membrane, which is made up of fat. If you put it into soap, that membrane is going to dissolve and that cell is going to die. So that's why soap is working so much here in this case. Now, coming back to our polarity thing. So first of all, we want to decide if the molecule is polar or not. That's different from deciding if the bond is polar or not. There's a question here. What about when you use a hand sanitizer? So exactly, guys, what is up with the hand sanitizer? So hand sanitizer is basically alcohol. And alcohol is also one of those things which can actually solubilize fat. Okay, so alcohol is also good at solubilizing fat, and that's how it's able to kill any living cells. Okay, so now. Okay. All right. Now, guys, coming back to our molecular polarity. Your molecular polarity, guys, depends on two things. One is bond polarity and one is symmetry. Okay. So the bond polarity, guys, is as simple as just looking at the bond and telling me the difference. If difference is more than 0.5, then that bond is polar. So you can say yes or no based off that. And then for symmetry also, you need to tell me if that molecule is symmetrical or not by saying yes or no. And we're going to see the example right now on when do we say something is symmetrical, when is something not symmetrical. So guys, listen to this part, okay? So I'm going to give you this example here. Does this molecule look symmetrical?
Yes.
yeah.
By symmetrical, what do we mean? We mean that you see this A is surrounded by the same atom. First of all, it's the same atom on all sides. And every side it looks at the top, left, right, or bottom, it looks at the same thing. So that's symmetrical. Let me give you one more example, guys. Here you have center A, you have X on top. On this side you have X, and on this side you have X. Now, you might think that if this is symmetrical or not. What do you guys think? If this is symmetrical or not, what do you guys think?
Yes.
Yes, this is still symmetrical. If you're thinking no, it's not, because you may be thinking you need on all four sides you need a thing. That's not the case. Now, what you need is you should have same things on all the sides. There should be no lone pair. So all atoms, all outer atoms must be same. That's your rule number one. And then your rule number two is no lone pair on central atom. Okay, so when you look at this A, guys, it looks at the top, it looks at the left or right, it looks at the same thing. So this is also symmetrical. So this is symmetrical. And so was this guy. This guy is also symmetrical. Okay, so everyone good so far?
These rules are just based on the symmetrical.
Yeah, these two rules are for symmetry.
Okay.
If these two rules are met, that there's no lone pair on the central atom, and all the atoms are same outside, then that molecule is considered symmetrical. Okay.
Got it.
Okay. Now, let's look at this CO2 example that we were working on. Now, guys, tell me if I ask you about the molecule polarity. So, guys, this is going to summarize what you want to learn here. Okay. So, listen to this example carefully. So, you have the CO2. We are trying to find the molecule's polarity. For molecule polarity, what is the first thing that we look at, guys?
Symmetry.
What do we look at?
Bond polarity.
The bond polarity. And what are you going to say? Is CO bond a polar bond or no?
Yes.
Yes, it is a polar bond. So guys, if the answer for the bond polarity is yes, then you go to the next part, the next question, which is what? If the molecule has?
Symmetry.
If it has symmetry or not. Now, what do you guys think? Does this molecule CO2 have a symmetry? Now, guys,
Yes.
again, yeah, it does. Now,
Same
see,
one.
if you look at the CO2 example, don't worry about the double bond. Don't worry about the lone pairs you see on the outer atom. Just look at this thing here. You see the CO is pulling this way. This CO is pulling this way. Do you see they cancel out each other?
Mm-hmm.
So this molecule is symmetrical. Okay. So what is your answer to symmetry? Yes or no?
Yes.
Yes. Now, guys, this is where pay attention to this point. We are trying to decide based off these two pieces of information if our molecule CO2 is polar or non-polar. So for the bond polarity, we are saying, yes, it is a polar bond. And that is indicating that molecule must be polar. See, if the bond is polar, then most probably the atom will be polar. But you have to look at symmetry. The symmetry, remember guys, symmetry is the enemy of polarity.
Oh.
It goes against polarity. Okay, so if the bond is polar and there is a symmetry, symmetry will go and cancel that polarity. So that will make the molecule not polar.
Okay.
Okay, all right, guys. If this was confusing, please let me know. I have no problem in explaining this again.
Can you repeat it once more?
Yeah, just repeat it, please.
Sure. So first of all, what are we trying to do, guys? We're trying to figure out the molecule polarity. For finding out if the molecule is polar or non-polar, we need to look at two things. One is bond polarity and the second is symmetry. We have to look at them together. So for bond polarity, we looked at the bond itself. We looked at this CO. You can pick any of those two. Just find the difference for one of them, and you tell me if the bond is polar or not. And you guys told me it is polar because the difference between C and O, C was 2.5, O was 3.5. Difference was 1, and that's more than that 0.5 that we learned. From 0.5 to 1.8, remember, was polar. So this is 1, and that makes the bond polar. Does that make sense so far?
Yeah.
Yes. So if the bond is polar, then you look at the second thing, and the second thing is the symmetry. Okay. So for symmetry, you look at the molecule if it looks symmetrical or not. So if the bond is polar and there is symmetry in the molecule, that symmetry will go and cancel that polarity. Okay, so remember that symmetry goes against the polarity. Okay.
So the molecule is not polar in this case.
Yes. So this tells us that the molecule is going to be nonpolar. And this is coming from the fact that the bond is polar, but there is symmetry which cancels the polarity. So guys, you can write that here, that symmetry cancels polarity.
And why does it cancel it out?
So you see this example, CO2 example?
Yeah.
So let me draw that again. So in the case of CO2, you see this oxygen is pulling this way,
Yeah.
and there's another oxygen pulling on the very opposite side. Why is it able to do that? Is because it's symmetrical. Because it is symmetrical, it cancels the polarity. Does that make sense?
Mm-hmm.
Yeah.
I have a question.
Yeah, question?
For number 1, for the bond polarity, are all compounds have a polarity, or
So
is it?
no, you will look at the bond difference. You look at the electronegativity difference between the two atoms.
So will there be a problem if the arrows go, if both the arrows go one way, then it wouldn't be symmetrical then, right? If
Yes. If that is the case, if both the arrows are pointing inwards, then symmetry is not there.
Got it.
But usually, remember, always the central atom is the less electronegative one, so arrows are usually always pointing outwards. Yeah. Okay. Now,
I had a question.
yes.
So if the bond polarity was, if it said no, and symmetry was also no, it would be a non-molecular polarity?
So if the bond polarity says no, just look if there's a lone pair or not.
Okay.
If there's a lone pair, molecule will be polar. If there's no lone pair and the bond polarity is no, then the molecule is nonpolar. Okay, so let me write that down. If bond polarity, so for bond polarity is no, and there is a lone pair, you have lone pair on central atom, okay? Then so the bond is not polar, but you have a lone pair, then molecule is polar. So guys, lone pair has the capacity to make the molecule polar. So the existence of lone pair will make the molecule polar. You got to remember that. Okay.
So, so that's carbon dioxide. So water, H2O, is polar. I mean, obviously, right?
Mm-hmm. Great. So guys, let's talk about this concept, and you might see a question on this on the exam. So water is polar, and we just figured out CO2 is what?
Carbon dioxide.
Yeah, CO2 is polar or non-polar?
Oh,
Non-polar.
It's
non-polar. Non-polar.
So do you think they're both going to dissolve into each other?
No.
Do polar and non-polar mix?
No.
No.
No, they don't mix. So how do you make soda then? Because soda does have water and it has CO2 dissolved in it.
You add. There's something else to it.
What is something else?
Carbonation.
Carbonation. So what does carbonation mean? Carbonation means that the process of adding carbon dioxide to water is called carbonation.
Yeah.
Carbonating the drink, right?
Mm-hmm.
But what actually happens is you took the CO2 and you forced it to stay inside under very high pressure. Tell me this, guys. As you open the can of the soda, does the CO2 stay inside, or does it try to escape?
Yeah, it escapes.
Makes
Okay,
sense.
it escapes. What is that telling you? That CO2 did not want it to stay in. It did not want it to dissolve. But the fact that you put it under high pressure and you close the cap, that is what is keeping the CO2 inside. As soon as you open the can, the CO2 is going to leave because CO2 is nonpolar. It does not want to stay in the water. Does that make sense?
Yeah, so that's why after 5-10 minutes of you opening a can, that's why it goes flat, right? Everything kind of escapes.
Because CO2 escaped. It did not want it to stay inside. Guys, does that happen with sugar? Does sugar also leave as you open the can?
No.
No. Because sugar, remember, was polar. It also solubilizes.
Mm-hmm.
The sugar dissolves in water. So no matter what you do, it's not going to leave until you, of course, you start heating the water. But if you just open the can, then the soda is not going to lose sugar. The sugar stays inside. CO2 is going to escape.